Hello again. So what we want to talk about today is the very beginning of the definition of computation. We want to talk about Turing machines. We're going to give a model for what it is that you can compute, and we're going to go through a couple of examples. Okay? Before we start, I want to talk a little bit about what a person wants to do to get the most out of these videos. So in the videos, we're not going to just go through everything in the book. That's what the book is for. Instead, what we're going to do is try to give an introduction to the material in the book, try to give a person some kind of understanding of what's to come. So if you are studying this material, you should go in something like the following order. If you're taking a class, of course you should go to class. If you're studying the material on your own, you might watch these videos first. So class, or these videos, or both, first. Second, you need to read the book. If you read the book a little bit before class, that's great, but you need to read the book in its entirety. You need to read the relevant section in its entirety closely after you see the lecture or the videos. That's very important. The book is not there just as a paperweight. It's there to be read. Third, you need to do the exercise. I can't overemphasize that just watching the videos is not enough. Just going to lecture, if you're a student who is taking a class and using this to supplement the material, just going to lecture is not enough. You should go to lecture, of course you should, but that's not enough. You need to do the exercises. The most important part is doing the exercises. If you are somebody who is studying this material on their own, great. I admire your persistence. I admire your industry. You need to try a good number of exercises. I've checked marked some for you to try, maybe 10 or 12 in each section, but in any event, you need to try a good number. You can't just look at it and then flip to the answer and look at the answer and say, yeah, I could have done that, because no, you couldn't. Or at the very least, you will from time to time find that you have fooled yourself. You need to try it. You need to say something like, oh, I just don't see what to do with the capital G here. What am I doing wrong? And then you look at the answer, and maybe the answer says, don't forget the capital G has to, I see now. And next time you come to a question involving capital G, now you have some insight into what's going on that you wouldn't have had otherwise. The way in which you grow is by trying the exercises. So enough finger wagging, but come on, you know that you don't get any better at painting or playing a violin or anything else if you don't practice. Doing the exercises is how you practice. So you go to class, watch the videos. That's your first phase. Second phase is reading the book. The whole point of the book is to be read. Third phase is doing the exercises, and the doing the exercises is the important part. Okay, so what we're going to do today. So we're going to mathematically precisely define computation. So before we do that, I have a little sort of introduction, little run-up, if I can find my mouse. Come on. There we go. Okay, so we are going to use as a model of computation Turing machines. It's a particular model. There's lots of models that a person could choose from. We have chosen this one for reasons that we'll talk about at the end. We have chosen this one, and we're going to go through it today. So in this class, the purpose of this class, a central question at the heart of this class is what can be done. I don't mean, if you have purple drapes, can you get away with a rust-colored rug? I mean, what can be done sort of scientifically or mathematically or computer scientifically, what can you do? So to bring the question into a little more focus, we want to answer questions and solve problems of the kind that we're interested. All of us in this room have certain interests. We want to be able to answer those questions and solve those problems. We like to think about questions in mathematics and computer science because that's who we are, or questions that are derived from the natural sciences because that's who we are, but we want to answer those kinds of questions. Just to try to get some kind of, sort of firm sense of what's happening here, think about this linear system. It is a mathematical computer science type of question. You might say to yourself, how quickly can I solve it? That's a computer science approach. You might say, I'd like to give all the solutions. That's kind of a mathematical approach. Finding a single XYZ that satisfies the system is great, no complaints. But surely what you really want to do is to find all of the solutions. So this is a list of all of the XYZs that satisfy that system. All of them. If you pick a Z like Z equals 10, and you plug it in 3/2 minus 1/2 times 10, 1/2 minus 3/2 times 10, and 10, you'll get a triple XYZ that solves that linear system. Every triple that solves that linear system is in this form. And of course, being who we are, we're really delighted when we can give a procedure that starts with the linear system and that ends with this complete solution of the system. And we're especially really delighted when we can give a procedure that's fast. So, when we ask what can be done, we're asking what can be done systematically, uniformly. I don't want to guess. I don't want to have somebody saying, you know, I noticed that if you take Z to be 0, then you can try that X is half Y. That's great. Noticing is great, but we want something that is systematic or uniform, algorithmic, something that can be done by a mechanism. So when we ask what can be done, we find ourselves saying what can be done kind of automatically. So we find ourselves saying what can be computed. And that's the kind of question that we like to answer. And again, my mouse has gone astray. There we go. Okay, the basic history of the subject. So in 1928, the famous mathematician David Hilbert and his student Wilhelm Ackermann proposed the Entscheidungsproblem. I apologize for my German. In German, it means something like a definite procedure. We want to know here, we want to know a definite procedure that decides from an input mathematical statement whether the statement is true or false. So nobody's ever going to say, you know, why do you want to know whether it's true or false? What people are going to ask, what do you mean by definite procedure? So, in mathematics and science, we have a culture. You know, we take Euclid's development as a paradigm. You start with axioms, biological processes, you build up theorems and lemmas, and you gradually get to a list of firm results. You're not allowed to just say, I see it. When I look at the picture, I see that those two lines are parallel. Instead, you have to prove that they're parallel following some kinds of rules. Those rules allow you to push around symbols typographically, meaning that you're just taking the letter A and substituting it for the letter W kind of thing. No unexplainable insights. This is not painting. You know, I mean, Van Gogh's painting these flowers. That's great, but that's not us. In our culture, a definite procedure is a sequence of fully specified steps that go from the input to the results. So the background for us is that verifying whether something is true or false requires what we today call an algorithm that you could put into code and run on a computer. Of course, in 1928, there were no physical computers. So an important question in the air at the time was to give a definition of what can be computed. What it is that you could compute mechanically or typographically or symbol pushingly. It's not a word, but... Okay, so we got to follow an approach. Different people thought about the question. We're going to follow the approach of Alan Turing. He described, his approach was to describe a mechanism that does the computing. As a prototype, he thought about it for a while, and he, you know, turned it over in his mind, you know, while you're eating breakfast or taking a shower kind of stuff. And he went one day for a long run, and he laid down on the grass, and he was looking up at the sky, and he had a kind of a picture. He imagined a clerk doing by hand multiplication on a big sheet of paper. Gradually, the sheet of paper gets covered with symbols. That's his prototype for a mechanical procedure. From that prototype, he thought of a number of principles that you want the definition of mechanically computable, this mechanical procedure to follow. So first point about the clerk, about that picture, is that the clerk has a piece of paper, that a mechanism should have a memory facility, like the paper, to store and retrieve information. You know, in those days, they didn't have physical computers, so they had people who did the computations. They called them computers. So we today would say it, but in those days, they would say he or she, have a memory facility, someplace where you can write down intermediate calculations and use them again later. Second, The computing agent, whether it's a person or whether it's a physical device, has to follow a definite procedure, a precise set of instructions, no room for creative leaps. Part of what makes a procedure definite is that the instructions don't involve random methods. You can't, run off a Geiger counter and listen to the click and say, if it clicks in the next 3 seconds, I'm going to do this branch. If it doesn't, I'm going to do this branch. That's not what we're talking about. Instead, we want the procedure to be definite. Now, you could hook up a device to a Geiger counter, but right at the moment, we're thinking about the device. The other thing that makes the procedure definite is that the agent is not using any kind of continuous methods or analog devices. I'm old enough that when I was a sophomore in high school, we were told how to work a slide rule, and you would look at the slide rule and you'd say, okay, I think I get, so that's 0.3. Is it 0.31 or 0.32? I can't really tell. Okay, well, that's a continuous device, and you're trying to guess whether it's 0.3. We're not doing that. There's no possibility here that you've misread the dial or anything like that. Instead, the agent is not working continuously. The agent is working discretely. Separate steps. Step 1, step 2, step 3. And they could pause between the steps, for example. If you say, well, time for lunch, they could pause between the steps and come back to it later. In those steps, we say that the agent has moved from state to state to state. If, for example, you're imagining the clerk who is multiplying numbers, then the clerk might say, well, the state I'm in right now is I'm carrying a 1. You could put that calculation down, say state 1, you note it on the piece of paper, and you come back later, oh yeah, state 1, I remember now. Those states will denote Q sub 1, Q sub 2, Q sub 7, Q sub 25, etc. So we will have a way to write down the states. We'll never use Q's for anything else because Q's are not all that convenient. The third condition, you imagine Turing laying on the grass and looking up at the sky and thinking to himself, okay, so what else do I need here? Turing wanted to imagine what's computable in principle. So he doesn't want to imagine what's computable on a device with 1K of memory, or 1 meg of memory, or 1 gigabyte of memory. He wants to study what's computable in principle. So he imposed no upper bound on the amount of memory. More precisely, he imposed no finite upper bound on the amount of memory. And you imagine that if the device is about to run out of storage space, that a little light comes on and the operator runs up and sticks some more on. So you're never going to run out of memory. There's no upper bound, no finite upper bound on the amount of memory. In addition, he imposed no upper bound on the amount of space you have for inputs, or space you have for outputs, space you have for scratch memory. So all that stuff, we want to know what's computable in principle, so we're going to leave that as unbounded. And finally, probably the biggest surprise, he left unbounded the amount of time that the computation can run, the amount of steps that a computation can perform before it finishes. So you can imagine it taking, more steps than there are, ticks in the universe, kind of thing. Okay, well, that's what he means by computing in principle. And the final question that Turing faced: how smart is the computing agent? Can it multiply, for example? Well, you say, well, I don't need the computing agent to be able to multiply because I can always just do repeated addition. That's a very mathematical approach to the idea, is to boil it down to its essential. It's just like going back to Euclid. You boil it down to its essential. What can we do with a minimum? Well, so you don't need multiplication. You can get away with just addition. What about addition? Can you go simpler than that? Well, you can just add 1 repeatedly. And in this way, Turing is paring the computing agent down until it is as simple as it possibly can be, while still able to do anything in principle that can be done. One advantage of being as simple as it can possibly be is that we can, in just a few minutes, just the minutes that taken up by this one video, show you what you can do with a Turing machine. If I tried to show you what can be done with a modern CPU, we'd have a big book with stacks and stacks of pages, and then there's this kind of instruction, and be careful when you're fetching from the queue. No. We want a device that is as simple as possible so we can understand it completely. So we're trying to do everything in principle. That's the whole key here, in principle. In principle. Okay? So a Turing device is a model. It's not intended to be a practical computer. It's intended to be a model of computation. So here's a picture. There's a box. It's got a start button so you can start the darn thing, and it's got a halt light so that you can tell when the thing is over. I put on the tape here, on the tape that's sticking out of the box, that's a paper tape because in those days that's what they had. I put two numbers that happen to be 74 and 72, separated by a blank, and I can imagine that this device is going to multiply those two numbers together. Inside the device, there's some kind of gears or levers or electronics or Legos. I don't really care. Inside the device is some kind of engineered thing that can do what I want it to do. So the tape is the memory, sometimes called the store. The box is the computing agent, sometimes called the control. We'll think of the box as a CPU, from analogy with a modern-day computer. The computing agent will get what it needs from the tape and also uses the tape as its scratch memory. So the box is the computing agent, and you start the button to set the computing going, and after a while, you know, buzz, 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 and then ding, up comes the red light, and we know that the computing is done. We look for the output on the tape. So it's very simple, very boiled down, very straightforward, no twists, no fetching from cues. Okay, so obviously there are some sophistications to it, but not much. So when you execute a calculation, the mechanism goes from state to state to state. You can imagine that inside the device is a dial, and it's got gears on it, and the machine settles in some gears. That's state 0. Then it moves over like so. That's state 1. Then it moves over like so. That's state 2. The agent transitions to a new state, to a new state, to a new state. This is not like reading a dial. This is like, you know, dun, 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 kind of thing. So, machine steps involve 4 pieces of information. You can call the present state QP and the next state QN. The other 2 pieces of information, capital T sub P and capital T sub N, denote the tape symbol that the read-write head is presently pointing to and what happens next with the tape. There's a little difference between TP. TP is a symbol. TN is what happens next. So TN is an action. The things that can happen next with the tape are, you can move the tape head left or right without writing. We'll call that TN equals L or TN equals R. You could write a symbol to the tape without moving the head. We'll use the actual symbol there. So if you wanted to write a 7, for example, we'll just put 7 in for capital TN. And you could write a blank. You can erase what's currently on the tape and just leave it blank. So as for the characters that can go to the tape, we'll just choose whatever's convenient. We often use blank and 1. The thing about blank is that we have this unbounded tape, unbounded in both directions. So it's got to have something on it. So I'm imagining that it's blank. So we're always going to need a blank. And so we're left choosing what the other character is. And often we choose a 1 in blank. But sometimes we choose 1 and 0 in blank. Sometimes we choose all the lowercase letters in blank. Whatever works, but we always got to have a blank. So that leaves us with that a single Turing machine, a sort of atomic component of a Turing machine, is a 4-tuple instruction. QP, TP, TN, QN. A 4-tuple instruction. For example, a typical instruction is Q3, 1, B, Q5. Q3, 1, B, Q5 is executed only if the machine is now in state Q3 and is reading a 1, that's the Q3, 1. And then the B, Q5 means that if that happens, then the machine will write a blank to the tape. I use B for blank. Sometimes I leave this tape symbol empty, but sometimes I use B, capital B, when I think that it might cause some confusion to leave it just empty. So capital B means write a blank to the tape, same thing as erasing the 1, and then move to state Q5. Okay, so what's happening here is a Turing machine is a collection of instructions. And the machine is just going to move from state to state to state by following the instructions. So all we have to do is a couple of examples to see if we can understand what's happening with following the instructions, and then we'll know everything there is, in some sense, everything there is to know about Turing machines. Okay, so let's get rid of the there we go, get rid of that picture and bring up the document camera. Okay, so I wrote down a Turing machine. This Turing machine is called a capital P sub pred, P-R-E-D. And it's got a bunch of 4 tuples. I think there are 1, 2, 3, 4, 5, 6 of them. I'm going to start the machine. There's the tape. That's how I draw a tape. I'm going to start the machine in state 0. I'm sorry about my handwriting. That's a 0. So that's the read-write head, and initially it points to the leading 1. 3 ones on the tape, and everything else is blank. And the read-write head, I write the state in the read-write head, just as a way of putting it somewhere convenient on the diagram. Okay, so let's try to understand what happens here. We are in state 0. We're reading a 1. So you run your finger along the instructions, looking for state 0, reading a 1. There it is. If you're in state 0 and you're reading a 1, it says move to the right and move the machine, change the machine over, change the gear on the inside or whatever works to state 0. Okay, so I'm going to write that down. I'm going to move the read-write head 1 to the right, and I'm going to put myself in state Q0, but I'm already in state Q0, so I'm going to keep myself in state Q0. So here's my picture of the tape again. Not a very good drawer. There's the 3 ones, except that now I've moved the head 1 to the right. Okay. And that's all there is to it. You just follow the instructions as they come up and keep doing what they tell you to do. All right, so let's see. So we're in state Q0 and we're reading a 1, so we find ourselves looking at the same instruction that we were looking at just a minute ago. State Q0, reading a 1, move the head to the right, go to state Q0. That is to say, stay in state Q0. Okay? 1, 1, 1. Move the head to the right, stay in state Q0. So that instruction, that Q0, 1, R, Q0, means something like scan past the block of 1s. So you can do some things with these instructions. Okay, so what happens next? Well, we're in state Q0 and we're reading a 1. So it says scan to the right, stay in state Q0. Oops, I'm out of room down there. Maybe I'll write down here. 1, 1, 1. I'm 1 to the right and I'm still in state Q0. Come on, there we go. Okay? So in state Q0, reading a blank now. So finally, something new. In state Q0, reading a blank. Well, in state Q0, reading a blank means go to the left and put yourself in state Q1. So we back up 1. Whoops. 1, 1, 1. Back up 1 so that the head is now pointing to the trailing 1 and put yourself in state Q1. So state Q0 meant something like slide all the way down past the 1s and then back up by 1. So we'll see what state Q1 means. State Q1, if you're in state Q1 and you're reading a 1, make it a blank and stay in state Q1. Okay? 1, 1. I could just leave a blank space, but it might be clearer to write a capital B, so I'll write a capital B. And stay in state Q1. Okay? So state Q1 means something like blank out a single 1. We're in state Q1, we're looking at a blank. State Q1, looking at a blank, move to the left and put yourself in state Q2. Okay, all right. 1, 1, remember there's a blank there. Move to the left and put yourself in state Q2. Okay, okay. All right, so I'm just following the instructions. The instructions tell me how to transition from step to step to step to step. So we could call this step 0 because it's when we started. This is one single step, so this is now step 1. This is step 2. This is step 3. This is step 4. This is step 5. This is step 6 we're on. We're in state Q0, excuse me, in state Q2, reading a 1. In state Q2, reading a 1. It's clear that these operations can be done by a mechanism. This is mechanical computing. In state Q2, reading a 1, move to the left, stay in state Q2. In state Q2, reading a 1, move to the left, stay in state Q2. So Q2 means something like scan to the left past the block of 1s. In state Q2, reading a 1, I really need a little extra room back there, so maybe I'll create extra room. If you're in state Q2 and you're reading a blank, that's where we are now. Move to the right, put yourself in state Q3. Okay, so again, mechanical operations. This is pretty much captures exactly what can be done with a mechanism. State Q3, reading a 1, there's no instruction for state Q3 reading a 1. There's no instruction for state Q3 at all. So we just stop because we have nothing else to do. We hold. Light the red light. We're done. And a person gets some glimpse of what's happening here. This is called capital P sub pred because it does the predecessor function. It scans past the block of 1s, backs up, changes the final 1 to a blank, and then scans left back to the beginning again, and stops. So there were 3 1s when we started, there are now 2 1s. This function finds the predecessor of whatever you gave it. If you gave it 5 1s, it would do the same operations except it would take longer, and we'd end with 4 1s. If you gave it 120 1s, I don't want to think about giving it 120 1s, you just would end up with 119 1s. Okay, so this does the predecessor function. Okay, so let's bring back the come on, there we go. So the set of instructions makes up a Turing machine. That's how we get from step to step to step to step. So this Turing machine, that's a Turing machine that was on the piece of paper. This Turing machine has 6 instructions, and I've typed it all out nice and neat so you can read. You don't have to read my handwriting. Typed it all out nice and neat, and we started out here in state Q. Started out here in state Q0, pointing to the first one on the tape, and then we press start, and the machine just started going. We, of course, walked through those steps by hand, but nonetheless, it was something clearly that a machine can do. I wrote them out again, all nice and neat, so that a person isn't confused about, what was he saying there on step 5? But it's all mechanical. And then finally you get to the bottom, and there's no state Q3, so no instruction applies, and the machine halts. So we can think of this function as we can think of this machine as computing the predecessor function. So the predecessor function takes its input. Predecessor function takes its input x and outputs x minus 1 if x is bigger than 0, and outputs 0 if x is 0. So you would have to go back and check with the machine on the previous slide. You would have to check that if the machine was started with 0 many 1s on the tape, the head is under a blank spot, what would the machine do? And what you'll find is that what the machine does is that it just leaves 0 many 1s on the tape at the end. Okay, so this machine computes a function that has an input-output behavior. And this is what a Turing machine is. It's a set of 4 tuples, and we like to think about what does it actually do. Okay, time for another machine. Let's see if I can manipulate all this stuff. Probably the answer is no. I got to turn off that and turn on the document camera. There we go. So I have a new machine. This machine is suggesting, the name suggests a little bit what it does here, p-add. So guess what? I have on the tape, I have 2 1s and then a blank and then 3 1s. And you can see blanks are kind of a problem. So I put a little underbar for the blank, but it's really not really a bit of a problem. So I generally will put a capital B. I'm going to follow it through, but you can imagine what's going to happen. At the end, there's going to be 5 1s. And the head is going to be back pointing to the first of the 5 1s. Okay. Okay, so here we go, just to go a little more quickly because let's face it, it's not really all that hard. So state Q0, reading a 1, state Q0, reading a 1, go to the right, stay in state Q0. state Q0, reading a 1, go to the right, stay in state Q0, 1, 1, 0, blank, 1, 1, 1. State Q0, reading a 1, go to the right, stay in state Q0. We've seen this before. We're scanning past the 1s. 1, 1, blank, 1, 1, 1, still in state Q0. So we scan past the 1s. If you're in state Q0 and you're reading a blank, state Q0 reading a blank, leave it as a blank and put yourself in state Q1. So you just change states, that's all. Go to state Q1 and do something different. Okay? So next step was to change to state Q1. 1, 1, blank, 1, 1, 1, to go to state Q1. State Q1, reading a blank, state Q1, reading a blank, mark a 1, so erase the blank and mark a 1, stay in state Q1. 1, 1, 1, 1, 1, 1, that was the blank, but we're changed it to a 1. Okay, state Q1, reading a 1, state Q1, reading a 1, leave it as a 1 and put yourself in state Q2. So this is a pure change of state instruction, just like we saw earlier, a pure change of state instruction. So we're seeing a couple things that you might do when you're programming Turing machines, to the extent that you really ever program them. So I need to change to state Q2. So 1, 1, 1, 1, 1, 1, state Q2. Okay? If you're in state Q2 and you're reading a 1, move to the left and stay in state Q2. If you're in state Q2 and you're reading a 1, move to the left and stay in state Q2. If you're in state Q2 and you're reading 1, move to the left, stay in state Q2. So we've seen this kind of instruction before, the scan backwards instruction. I lost track of the number 1. There we go. I think I'm there. If you're in state Q2, you see a 1, scan to the left. Can you guess what's going to happen now? I'm going to back up and erase that 1. So I'm in state Q2, I'm reading a blank, state Q2 reading a blank, leave it as a blank, put yourself in state Q3. Slide this up just a little bit, leave it as a blank, put yourself in state Q3. It doesn't quite make it on the page. If you're in state Q3 and you're reading a blank, if you're in state Q3 and you're reading a blank, there it is. Go to the right, stay in state Q3. And if you're in state Q3 and you're reading a 1, if you're in state Q3 reading a 1, change it to a blank, put yourself in state Q4. Whoops. There we go. Put yourself in state Q4. And of course what you see is I now have 5 1s on the tape. I don't yet have the head pointing to the first 1, but I have 5 1s on the tape. That's what I wanted. I start with a 2 and a 3. I want to end with a 5. Okay, so state Q4. State Q4 says if you're looking at a blank, move to the right, put yourself in state Q5. And I need to slide the paper. I apologize. You're in state Q4. Three, 4, 5. Put yourself in state Q5. Okay. So state Q5 reading a 1. There is no state Q5 reading a 1, so I stop. So I halt. Okay, so again, started with a 2 and a 3, separated by a blank. You got to separate them by something. How's the machine supposed to know that they're different? Started with a 2 and a 3, separated by a blank. Certain amount of pushing symbols around, typographic manipulation. Never did I have to think about what would be a good idea. And I end with 5 1s on the tape. Okay, so this machine is, I called it P sub add, and I call it P sub add because it adds the two things on the tape together. Okay, so I'm thinking about a particular machine, That's the machine we were just looking at, and here's the steps that we went through. Okay, wrote them out nice and neat so a person could see what they do. Now you probably noticed that on the previous couple of slides there were some pictures. So when we describe these machines, a lot of times we don't use the set of 4 tuples just because it's a little hard to read, no more complicated than that. So instead of the set of 4 tuples, we might use either a table or we might use a picture. Neither of them is especially hard, they're just easier on your eyes, that's all. So for example, for the machine, if you're in state Q0 and you're reading a blank, then you're supposed to move to the left and go into state Q1. Well, right here, Q0 and reading a blank, you're supposed to move to the left and put yourself in state Q1. So this is just simply a kind of an organized picture of what the 4 tuple are saying. The present things here, this present state and the present symbol on the tape, are on the outside of the table, and on the inside of the table is what happens next. One thing that this table highlights is that the relationship between input and output, what you're looking at on the tape now and what happens next, is a function. So you take Q0 and B, and then there's a thing to do. You go to the left and put yourself in state Q1. That function is called delta. We'll talk about it a lot as we move through the course. Now for the diagram is just exactly the same thing. If you're in state Q0 and you're reading a B, then you're supposed to go to the left and put yourself in state Q1. So it draws an arrow from Q0 to Q1, and the action, the capital T sub P, is written there with a capital L. On the other hand, if you were in state Q0 and you were reading a 1, then you're supposed to stay in state Q0, so you write a little circle that goes from Q0 to Q0, and a 1 and an R indicate the 1 and the R. So just a different way to draw the machine, to describe what the machine is, just simply easier on your eyes than the set of 4 tuples. For the addition machine, it's exactly the same thing. You see the function here, and the function is a little hidden here, but you see the diagram. These diagrams are good when there's not many states in the machine. When there get to be more than, how many states in the machine here? 6 states. When there get to be more than, say, 10 or 12 states, the diagrams get to be a little hard to read, so we kind of stay away from them. This is good for describing the function between the present and next situation for the machine. The present configuration of the machine and the next configuration of the machine. This is very good for describing that function, and we'll use it for that purpose later. Okay, so we've seen 2 examples of machines, and they're not super hard. I mean, a person just follows them through. Now there are some programming techniques that you might want to become familiar with, but it's not really super hard. Okay, so we want to close with a couple of points. First point, a crucial observation that we'll talk about a lot as we move through the semester. Some Turing machines, for at least some starting configurations, don't halt. So here's a machine, I drew it with the little circles, but anyway, here's a machine that never halts, regardless of what you give it. It's a little harder to read here than it is when you look at the diagram, so let's look at the diagram. You start in Q0 because you got to start somewhere. You press the start button. Something's on the tape, maybe either blank or a 1. If there's a blank on the tape, then the machine goes back into state Q0. That's what this says. Machine goes back into state Q0, and it's still pointing at the same blank it was pointing at a second ago. So this machine will just keep step over and over again. It will never halt. It so happens when I drew this machine that if there's a 1 on the tape, the same thing will happen. Step. The machine will just never halt. It never gets to a state for which there's no instruction, so it will never halt. Some Turing machines don't halt. We will ask ourselves, as we move through the subject, we'll ask ourselves, what can you do to detect that? And we'll spend a lot of time thinking about it. Okay, so that leaves us with the definition of Turing machine. And we're going to talk more about the definition of Turing machine in the next slide. But in the next video, but I just wanted to close with the definition up. What you see, once again, just to emphasize what we talked about through the video, a Turing machine is a set of 4 tuple instructions. There they are: QP, TP, TN, QN. QP is a state like Q5 or Q7. QN is a state like Q5 or Q7. TP is a symbol on the tape. It's what you're looking at on the tape. TN is a little different. TN is an action. It might mean move left. It might mean move right. It might mean change the symbol that's currently on the tape, that you're currently looking at with the read-write head. And finally, when we look at the definition of Turing machine, one of the things we'll find is that the definition of Turing machine has an instruction. We take the present state and the present symbol we're looking at, so that's QN, capital TN, and from that we will either have a character or an instruction to move left or right and a state. So we have a function that governs how this machine works, and the instructions just tell you what the function is. Do this, then do this, then do this. Okay. So again, when we start the next video, we will be looking at the definition of Turing machine and working through a couple of details. But the takeaway from this video is the purpose of a Turing machine is to be possible to understand. You can understand this machine in, I don't know, 20 minutes, 30 minutes. It doesn't take a week of careful study of the instruction book. You can understand what this machine is doing. It's clearly mechanical. You can clearly make a device to do this. And when you think back to Turing's 4 principles, this machine satisfies those 4 principles. There's a place to store things. There's an unbounded computation. And the CPU, we'll have to convince ourselves, but the CPU, the control, can do anything you can ask of it, anything you think to ask of it. Okay, so in some sense, in a half an hour, we've seen everything that you can do in the mechanism. So that's a big step forward. Okay, all right, so see you for the next video. Hope you found this useful. Okay, bye-bye.